Now we will start the second part of engineering mechanics that is very important, that is dynamics. So as we already discussed, dynamics, that is a branch of mechanics, deals with the bodies which are in motion. So dynamics deals with bodies which are in motion. So basically in dynamics we will deal with the problems where the bodies will be in motion. But there are two ways for analyzing the bodies which are in motion. In one case we have to consider forces or couples which are responsible for motion, and in the other case we are not considering the forces and couples which are responsible for motion. So according to this consideration, we can further divide dynamics into two categories. One is kinematics, and second one is kinetics. So in kinematics, we are dealing with the bodies which are in motion, but we are not considering the forces and couples responsible for motion. So forces and couples, without considering forces and couples which are responsible for motion. For motion. So I will again define the kinematics. It's the branch of dynamics deals with the bodies which are in motion without considering forces and couples which are responsible for motion. Similarly, in kinetics, we are dealing with the bodies which are in motion, but we are considering the forces and couple which are responsible for motion. So, considering forces and couples which are responsible for motion. So I will again define the kinetics, that is a branch of dynamics, deals with the bodies which are in motion with consideration of forces and couples which are responsible for motion. Now at this part of time we are first interested in kinematics. So we will start with kinematics, and in kinematics we will see kinematics of rectilinear motion. Rectilinear motion means motion in a particular direction in a straight line. It may be along x direction, it may be along y direction, or it may be along z direction. So basically in kinematics of rectilinear motion, we will deal with the bodies which are in motion on a straight line. Similarly, one more category in kinematics, we will deal with kinematics of curvilinear motion. So we will deal with the curvilinear motion. So in which we are interested in motion of a body in a particular plane, like projectile motion. So the example here, projectile motion. So basically in kinematics we will see two kinds of motion. The rectilinear motion, which is basically deals with the straight line motion, and second one is the curvilinear motion, which deals with the bodies in a plane. The projectile motion is a very good example of this curvilinear motion. So let's start with kinematics of rectilinear motion. In kinematics of rectilinear motion, we will see the motion with uniform acceleration, and we will see the motion with non-uniform acceleration. So we are having two things: motion with uniform acceleration. With uniform acceleration means acceleration will not change with respect to the time. But in case of non-uniform acceleration, the acceleration will change with respect to the time. So how we will use the equation in case of motion with uniform acceleration and motion with non-uniform acceleration. So these two categories, these two motions are different. So one by one we will take these motions and we will see which kind of equations are applicable for motion with uniform acceleration and which kind of equations are applicable for motion with non-uniform acceleration. So let's start with motion with uniform acceleration. So motion with uniform acceleration means acceleration is constant. So I am denoting acceleration by A, means A is constant. So the rate of change of A with respect to time will be zero in case of motion with uniform acceleration. So we are having three equations we can use only when the motion with uniform acceleration. This is V equals to U plus AT. Second one, S equals to ut plus 1 by 2 at square, and third one, v square equals to u square plus twice as. So these three equations are very useful when the motion with uniform acceleration. So but remember one thing, these three equations are applicable only when motion with uniform acceleration. Uniform acceleration. So my appeal is, whenever there is a motion with uniform acceleration, then only you can use these three equations. That is nothing but v equals to u plus at, s equals to ut plus 1 by 2 at square, and v square equals to u square plus twice as. I would like to give the description of this notation. Here u is initial velocity, v is final velocity, A is acceleration or retardation, T is time, S is distance or displacement, so these are the explanation of the terms we are using for these three equations. Now in case of motion with non-uniform acceleration, so with motion with non-uniform acceleration we can't use the previous three equations, because in that case acceleration will change with time, means acceleration is not constant. So in that case we have to use these things, like for velocity, that is nothing but v ts by dt, here s is the displacement. For acceleration we can use dv by dt, or one more equation we can use, that is v dv by ds. So these things we can use for solving the problems where the bodies are moving with non-uniform acceleration. And here we will talk about instantaneous velocity and instantaneous acceleration, because at each and every instant the velocity and acceleration will vary. So in that case, means that in case of motion with non-uniform acceleration, we are interested in instantaneous velocity, instantaneous acceleration. So we have to use either integration or differentiation for solving this kind of problems, and we have to use these equations in terms of differentiation here, that is v equals to ds by dt, and acceleration is nothing but dv by dt, and the one more formula for acceleration is a equals to v d. Let's take a problem based on kinematics. So I am just writing the problem here. The problem states like that: the brakes of a train reduce its speed from 60 to 20 km per hour while it runs 200 meter, assuming that there exists constant retarding force. So now we have to find, number one, how much further the train will run before coming to rest. Before coming to rest. Second thing, how long will it take? So here in this problem that is given, we are applying the constant retarding force. The meaning of this thing is that this problem is based on motion with uniform acceleration, or we can say that motion with uniform retardation. Here the speed, that is initial and final speed, is given, and the distance traveled during this initial and final speed is also given. And now we are interested in the distance traveled by the train before stopping, and how much time it will take to do this activity. So here for solution, first write the given things, that is initial speed is given, noted by u, 60 km per hour. Final speed is given, that is 20 km per hour, and the distance traveled during this thing is 200 meter. So in terms of kilometer, we can write 0.2 kilometer. And now we will apply the equations v square equals to u square plus twice as. So by this way we can find out easily the acceleration. If it is coming negative, it means it's a retardation. So if we put the value of v, that is nothing but 20 km per hour, that is 20 square equals to 60 square plus 2a into 0.2. So 20 square is nothing but 400. This one is 3600 plus 2a into 0.2. So 400 minus 3600 divided by 2 into 0.2 equals to a. So a will be minus 3200 divided by 0.4 equals to minus 8 1000 kilometer per hour square. So this sign is coming negative. It means it's retardation, which is already mentioned in the problem. Now, when train will stop, at that time final velocity will be 0. So again apply the same equation, that is v square equals to u square plus twice as. But here in place of v, now we have to put 0 because we are interested in the distance traveled by the train when it will final stop. So u we already know, that is 60, so 60 square plus 2. A we know, that is minus 8000 into S. So now we are having 3600 minus 16,000 into S. So S will be 3600 divided by 16,000. So this value will come 0.225 kilometer, or if we multiply it with 1000, it will come 225 meter. So the correct answer for the first part means how much further the train will run before coming to rest, that is 225 meter. So the 225 meter is the total distance traveled, total distance traveled before stopping was to 225 meter. But we are interested in how much further the train will run, because already it ran up to 200 meter. So further distance traveled will be 225 minus 200 equals to 25 meter. So if we are interested in how much further distance traveled by the train, it will be 25 meter. And if you are interested in total distance traveled before stopping, that will be 225 meter. Now for second part, we are interested in time. So we can use the equation where we are having the term t. So we can use v equals to u plus at. We know when the train will stop, v will be 0. So 0. We know the value of u, that is 60. That is 60 kilometer per hour. We know the value of a, that is minus 8000. We know the value of, now we have to find out the value of t. So now we will solve it. We will get t equals to 60 by 8000 hours. And if we want in seconds, so we have to multiply it with 3600 seconds, because in 1 hour there will be 3600 seconds. So this value will come 27 seconds. So this one is the time taken by the train when the velocity will decrease from 60 km per hour to 0. Suppose we are interested in the time t when we want to know the time when the speed of the train will decrease from 20 kilometers per hour to 0 kilometer per hour. Means we want to know the time interval where the distance traveled by the train will be 25. Means initially the distance traveled will be 225, and finally initially the distance traveled by the train will be 200, and finally it will be 225. So here we are interested in the time taken by the train when the speed will decrease from 20 km per hour to 0 km per hour. So our final speed will obviously will be 0. So again we have to apply the same thing, v equals to u plus at. So v is 0, Here u is 20 plus we know that is minus 8,000 this acceleration and time. So t equals to 20 by 8,000 hours, and if we want in second then we have to multiply it with 3600, and if we solve it then the answer will come 9 seconds. So by this way we can get the value of time. So the time in part 2 and time in part 3 is different. In part 2 it is coming 27 seconds, and in part 3 it is coming 9 seconds. So these are the two different times. Here in part 2, the time taken by the train when the velocity will decrease from 60 km per hour to 0. In part 3, that is the time t taken by the train when the speed will decrease from 20 kilometers per hour to 0 km per hour. So according to the problem or according to the given velocity, we have to calculate the time. So I am just showing how we can calculate time for different speeds. Now take the second problem, which is based on problem based on kinematics. I am just writing the problem. A particle is dropped from the top of tower 200-meter high, and another particle is projected at the same time vertically upward from the foot of the tower, so as to meet the first particle at a height of 50 meter. Find the velocity of projection of the second particle. So here in this problem, a particle is dropped from the top of tower 200-meter height, and another particle is projected at the same time vertically upward from the foot of the tower. So the first particle will meet at a height of 50 meter. Now at that time the first particle will meet with the second particle at a height of 50 meter. So now we have to find out the velocity of projection of the second particle. So solution of this problem. Let's assume particles will meet after t seconds. So first we will analyze motion of first particle. So first particle will be dropped from a height of 200-meter tower, and it will meet with the second particle at a 50-meter height. So the distance traveled by the first particle for meeting with the second particles at a height of 50 meter, it will be 200 minus 50, 150 meter. So the first particles will go for downward motion of 150 meter. So here we are assuming the direction as per as our sign convention. Positive y is positive, negative y is negative. It means downward is negative, upward is positive. So now I am applying the equations which is used for motion with uniform acceleration. So here the first particle is moving under gravity, means the acceleration is nothing but acceleration due to gravity. So it is constant. So we can use the equations for motion with uniform acceleration. So let's use the equation s equals to ut plus 1 by 2 at square, and as here the distance traveled by the first particle we know that is 150 meter but is in downward direction. So it's minus 150. So let's say s is displacement, and it will be good in place of distance. So displacement is 150, negative sign shows it is in downward direction. Initial velocity, when we are dropping something from a certain height, so the initial velocity will be 0. So u is 0 plus 1 by 2 for motion under gravity. Acceleration will be nothing but acceleration due to gravity g, it is acting in downward direction, so negative t square. So here we are having 150 equals to 1 by 2 gt square. So t will be 150 into 2 divided by g. So it will be 150 into 2. We know the value of g, acceleration due to gravity, 9.81 meter per second square. So this thing will come 5.53 second. So the value of t is 5.53 second. So now let's consider motion of second particle. Motion of second particle. The second particle is moving in vertically upward direction and it's covering displacement of 50 meters. So now we can apply the same equation we applied for motion of first particle, that is nothing but s equals to ut plus 1 by 2 at square, and here we are projecting the second particles with some initial velocity. So now we are interested in the value of u. As we know that is 50 meter, it is in upward, so positive. U we have to find out. T we know. After that, after solving the equation, we will put the value of 2 t plus 1 by 2. Here motion is again motion under gravity, so acceleration will be g and it is acting in downward direction, so minus g t square. So here we are having 50 equals to u2 minus 1 by 2 gt square. So we know the value of 1 by 2 gt square is nothing but 150. So we can put here the value of 1 by 2 gt square. It is nothing but 150. 50 equals to ut minus 150. So ut will be 50 plus 150 equals to 200. So u will be 200 divided by t, and we have already calculated the value of t. It's nothing but 5.53 seconds. And if we divide 200 by 5.53, then we will get 36.17 meters per second. So the velocity of projection for the second particle in upward direction will be 36.17 meters per second.